Okay. Good afternoon. So, I believe you guys have a class in the morning, right? Okay. Yeah. Okay. So hopefully we are not falling asleep. Although what we are going to finish in today's class is a little bit similar to what we are doing in related rates. So the related rates. So you will see some words and some solving problems within those. We call the optimization. So I will finish the L'Hopital, the indeterminate form. But before that, I think last feedback. My original answer was correct after all. So it's supposed to be a 4 asymptotes. Okay? So 4 asymptotes. I think I also attached this in the Moodle, so you can take the notes. So what I want to emphasize is when we have this, the limit problem, if you remember, when we have this square root, remember that the square root can be positive or negative. Depends on what we are going to approach. Right? When we approach going to the line, so we are going to look on the more negative side. So this one will be a negative. So when we square root this will have a negative result. Right? So that's why it's negative. And if you try to draw in a maybe GeoGebra or other software, you will see that it's supposed to be 4 asymptotes. Yeah. I was afraid that yesterday I was wrong. So really 3? Okay. But I checked, and then one student asked me that it's 4 asymptotes. So it's actually my original answer is correct. Okay. Yeah, I forgot the graph, and I also tried to see the graph, and yeah, this is correct. Okay. Let's see what we have. Yeah. Last time we are having the indeterminate products. Okay? Indeterminate products. So the idea behind this indeterminate products is basically we are forcing this supposed to be zero infinity problem. We are forcing out that this equation becomes 0 over 0 or infinite over infinite. And because of that, then the L'Hopital rule can be applied as well. And I think most of the problem within all the cases in L'Hopital rule is the same. Okay? Because the L'Hopital rule is basically be applicable when you have 0 over 0 or infinite over infinite situations. So this is case 2. So let's go through all 4 cases, and then we have I think a little bit examples, and then move on to optimizations. Yeah, now is case 3. We call the indeterminate differences. So this is when, for example, if we have limit of f, okay, and the result of this limit is infinite, and we also have a limit for other function, let's say g. This is also infinite. If we combine these two, now this problem becomes infinite minus infinite, right? So this is what we call the indeterminate difference. So again, the indeterminate forms means that we are not really sure what is going on. So we cannot really determine what forms that is and how the value will be. Okay. So if we take this infinity minus infinity, yeah, probably if you think that infinite is a concept of value, then well, you will answer, oh, this will be 0. But remember, always remember, that the concept of the infinity is an abstract concept. It's not a value. So you will not you cannot minus this and becoming 0. Okay? So if you do this, let me write here. If you do this, then this is very wrong. Okay? Don't do this.
I don't think
No. Don't ever do that. Okay? So let me give you a quick example. Let me give you a quick example and how to look at the questions. Let's say we have a limit that x is getting closer to 1 from the right side. Okay. If we take sometimes to look at and observe just from the algebra and substituting 1, we see that this is infinite. The other part also becomes 1 over 0 or infinite in terms of limits. So this is actually applicable. This indeterminate form is applicable. And then what we are going to this differences, any idea? Yeah, a little bit. How can we look at this?
first we should do it like a single.
Yes. So we need to combine this together. So the idea is still the same. We need to force out all the forms, all the fractions to be in 1 and make it 0 over 0 or infinite over infinite. Okay. So what we are going to do is we are going to combine this all together. So we have x minus 1 minus ln x. If we check, then this will be 0, right? We check 1, this also 0. So this is applicable. So 0 over 0. So after this process, then perhaps we can take L'Hopital. Okay? So we can derive the top, derive the bottom. We take L'Hopital. So every time you take L'Hopital, usually we are going to take some like the symbols, okay? Which means that we are going to do some L'Hopital rule here. So let's derive one by one. The top equations become 1 minus ln becomes 1 over x, right? And the bottom equation, ln x, this is can do some product rule. Okay, product rule. So we have 1 over x. So 1 over x and x minus 1 plus ln x. Okay, so let's do some simplifications. So this will be 1 minus 1 over x for this one, right? So to simplify these fractions, let me multiply this with x over x, just to remove the 1 over x. So x minus 1, and then x minus 1 plus x ln x. And then do we still have problem? I think we still have 0 over 0. So one more time, it's okay. So we can do L'Hopital as many as we want. Yeah. So not only one time. So you can do this 2 times, 3 times. Every time you see it's still 0 over 0, you can do more. Okay, you can do more. But usually maybe the maximum you take maybe 2 or 3, the maximum. Frequently just 1 time, but the maximum that you can do in average maybe 2 to 3, the maximum. So do one more L'Hopital. So we have this become 1, this become 1 plus ln x plus x over x, right? Or we can write x over x become 1, right?
1 over 2, yeah.
Yes, it's 1 over 2. Okay. So no matter what type of indeterminate you have, the idea is to force out the fraction 0 over 0 or infinite over infinite and then do derivative. Always like that in indeterminate form. Unless some problems that maybe not required, you don't really need to do some calculation, but you need to have some logical reason to answer. For example, let me just write questions here. Okay, so limit e to the power of x and minus x. This, if we see just by substituting this x, we see that okay, it's infinite and it's also infinite. But how do we can answer this? At least 2 methods, not methods, 2 perspectives. Anyone have idea? Yeah, just take the limit.
You cannot say things by infinity. You have to prove it.
Yeah. Yeah, it's a little bit. This is not required any calculation.
Maybe we can rewrite x as e to the power ln x. No. No, it's pointless.
The first perspective, you can argue that exponential will go faster if you compare it to the x. And of course, that this is significantly larger than x. So you could say that this is supposed to be infinite. Because x will be insignificant, will be like really low. We can answer like that. Or if you want to look more analytical, we can factorize x and make it more like this. You will see that when we have this e to the power of x over x, if you also try to look at it visually, this is really logical. So we are going to have we are going to have this limit. Okay, we will for sure it will be going to be infinite. So we know that this is going to be an infinite number. Okay. Yeah, sometimes you need to have like a good perspective to see. Yeah, maybe I will giving you some some introductions, like sentence to guide you through the answer. Okay, so that's the indeterminate differences. Okay, if we need more exercise, well, we can have. But I think I will focus on just give you all the types first, and then maybe later we can have exercise. And perhaps the exercise, maybe I will give you, like in the Moodle, okay, for this chapter, along with the quiz. Okay, along with the quiz, I already, I think, finished the questions. Okay, before we continue, is there any question? Anything to discuss? I think this part, I think, not really located. This is just mostly this is what will happen. You are going to combine some fractions. You will see something, and then you need to force out that it's going to be 0 over 0. All right. Okay. The last case in this L'Hopital we call the indeterminate powers. And within this indeterminate powers, we have another 3 cases. So let me go through one by one. So the first one is when we have 0 with power 0 situations. Okay. Because if we force out our definition on 0 and limit, something with power of 0, we know it's 1, right? Something 0, power with any numbers, it's 0. So is it 1 or 0? That's become indeterminate. So we cannot determine what it's really like. The second one when we have an infinite with power of 0. Okay, the last one so limit so the last one is when we have 1 with power of infinity. This is also indeterminate 0. But there is an exception. So except all is indeterminate forms except the 0 with power of infinity. Okay, if I have time, I will explain. Okay, this one. Okay, so there is three cases. 0 with power 0, infinite with power 0, and 1 with power infinite. Maybe you will be asking why this is also considered as indeterminate forms. I think after this page I will explain some questions that related to this. If you remember that we might have questions that maybe we have, like, for example, limit, okay, and this is maybe 1 plus something, maybe 1 over x, and then this is having another x squared, and then maybe 1 over x squared, and x is going to be 0 like that. Okay. If you think carefully, this becomes what we have here. So if I'm writing, if we see 1 with power of 30,000, okay, let's just say it's 30,000, or maybe 300,000. What will be equal? 1. Sure, it's 1. Okay. The problem is when we deal with limit, we deal with something that is not really we can comprehend. Okay? If you want to make something maybe 1 with power of and using limit like this one, we are not really sure what will be going to happen here unless we solve this and take some L'Hopital rules. Okay, I will explain that a little bit later. Okay? So all this part, okay, 0 with power 0, infinite with power 0, and 1 with power infinity, we can solve within the same techniques, okay, that we also have done the techniques in derivative. That is, we are going to use ln. We take the log. Why? Why we need to take the log? Because we want this to come to the front. Okay. So let's try to look at the equations. Let's just see a couple examples. If we want to compute limit, let's say x with power of x. Okay, now we for sure this will be 0 with power 0 situation, right? Okay. At least, okay, it depends on which method you prefer. Both are using the ln. Both methods. I will always show you two perspectives. The first perspective is writing the this power in terms of e. So we are going to take e and take ln and x power of x. Okay, we can do this. And because e is a constant, then the limit only consider on this power. So we can take this limit up here. Right? Okay. So we take e, so we can write e with power of limit. And then we just take, and then we can write this ln x power x, x ln x. Okay. And this is, I think we already done this before, right? So if you want to write again, that's okay. So we can write this in terms of this. And this is can be L'Hopital, right? So we can do L'Hopital. So 1 over x over 1 over x squared. And this will be equal to e with power of 0, which is 1. If you feel maybe not really comfortable writing using e, using this transformation, I think using equaling this x to the power x with y or any variable, and then take ln, it's also okay. It's also okay. We can write down. So maybe let me write this a little bit left. Maybe right here. Okay. So let y is x with power of x. Okay. And then take ln of y, and then take ln for x with power of x. Okay. And then take limit. And then x can be placed in front like this. And then the same thing. This will be resulting 0, right? But remember that this 0 is our element. Okay. So y. So limit of y is e with power of 0, which is 1. Okay. Okay, let me give you maybe another couple example. Limit as x approaching infinity. 1 plus let's say ln 4. Okay, this is the same idea. Okay, so every time you have a indeterminate powers, what you need to do is you need to place the power into the front by take the log or ln. Okay. So we can let the, let's say y becomes this. And then take ln. Maybe let's write with red. And we can write down that the ln y is x ln, or let me write it a bit right,
ln 1 plus 4 over x. And then take limit okay. Now we can focus on the right side that we
see that this becomes 0 multiplied with infinity, or the indeterminate product. This becomes 0, right? This becomes infinity.
so we can force out this part and make it 0 over 0 or infinite over infinite. The key is the same, so we might, well, we can try one by one which one is the one that we're looking for, but I think this is the best way to check.
So when we have this, we have 1, which is 0, and this will be also 0. So 0 over 0. 0 over 0.
And then we can take this into our L'Hopital rule. Okay. So the bottom part is negative 1 over x squared with the derive. And the top equations become 1 over 1 plus, okay, and then multiply with derivative of the inside one is negative, let me write with bracket, negative ln 4 x squared, right?
I will move this going up, then canceling with this, and minus with minus.
So we have, so we will have, let me write here, ln 4 over 1 plus ln 4 over x. And we put the substitution infinity inside x, it's become 0, so this will be equal to ln 4. But it's not the final product. Okay? Remember,
What we did is the ln 1. So we have y equal to e with that ln 1.
sometimes
Students will stop until here and not stop with ln 1.
so this is ln limit, this is ln y. So I will write here that limit x going to infinity of y is e with power of ln 4 or just equal to 4.
process here. Just canceling this, canceling the minus. Yeah. And then just leave out this 4 over x because you are going to put x inside, right?
Okay, I got it. Yeah, we just do it.
Yeah.
Let's just start it right now.
Yeah, just multiply the top and the x. Yeah.
Yeah, I just did it.
Okay, any question? Before, usually the weather is a little bit warm. We turn on the AC, we feel like we are going to fall asleep. But anyway, that's okay. I also have that experience, especially when you have been like maybe after you doing some really tiring classes. You're welcoming by this all this equation and yeah. Anyway, the next part is I want to show you a proof that why the 0 with power of infinity is not inclusive here. Let me show you how.
Okay, I hope this part is you already guys finished. So let me introduce you to the proof. Okay, suppose f is a positive function. Okay, positive function means it's always positive. Okay, it's always positive. And if the limit of this f is 0, and we have another function g, and this g, the limit is, let's say, with infinite power. So when we take this limit and make it f of x with power of g, now we find our form 0 with power of infinity, right? So based on the information that we have this positive function and we have this, and all this stuff here, let's break down our limit using our method, the same method that we take in the previous page. Okay. So let y equal this, and take ln. So take ln, let me write in here. So take ln, both sides. So let y is f of x. Okay. So ln of y is become g of x ln f of x. Since f of x is a positive function, right? Then our ln has no problem, right? Because ln is, if you think on the domain of ln, and if we maybe take some illustrations to show how this ln will be applied. Okay, perhaps this is an illustration to show that okay, ln f of x is fine, right?
It's on its domain because it is a positive function. So all possible x that put inside the f will be a positive. So ln with positive number is okay, right? It's on its domain. Okay, so not a problem.
So we can write that ln f of x is defined, okay? Or domain, or maybe just ln of f of x is defined is okay. Now we take the limit of this ln y, take limit also this part. So g of x ln of f of x, and if we take the limit, when we take the limit, remember that
when we move x closer to a, if you look at our trends, where will be going? If we go from to the directions the left side, it's going down, right? It's going down.
So this will be equaling to negative infinity. So first, let me write again that from the informations that the g of x is infinity, and limit of f is 0. Okay, so and limit, or let me write here, and limit I think we need to write here first. Okay, let me write, if let's say variable t is equal to ln y, okay, and if we have limit x to a y, this is, we can say t goes to negative infinity of e power t. And this will be equal to 0.
Why limit x equals to x, this one is equal to negative infinity?
Okay.
Let me explain here. That this is comes from so because of the okay, because of this
ln f, if this is ln f of x, we define this as our ln. If we take our limit as x getting closer to some a, and if we take that and if we imagine if the direction go to the left, we see that it's going to go down here, and it will affect the
yeah,
the ln f of x, that it will be equal to negative infinity. Okay? So all the way that when we have g and multiply with ln f of x, it will also affect the sides in which it will be going down. Okay?
so if we take this, okay, from our illustrations, if we rewrite this in terms of e, or maybe let me write this from the g f of x and power of g of x. This is in turns is equal to e with power of g of x ln f of x. Okay. In turns, that this will be equaling to limit, or maybe e, and this is limit as x approaching a of or maybe let me just write directly here. Let me just write here that this will be equal to, this one is going to be negative infinity, and we will have the 1 over e with power of infinity. So if we take this into our e, let me draw. And this is e to the x, this is e to the negative x. Okay, we will continue after the break, okay?
And actually, I understand.
Okay, so let me
Summarize what we've done first here. So what we have done is when we have this gx is infinite and f of x is 0, and when you think on the limit, when we have the f of x inside the ln, we are going to have this direction now. So when we approach to f of x, if it is getting 0, like in here, then it's going to be negative infinity. And when we have this in one equation, it will force out all this equation to be going down because of this negative infinity. Okay? So that means if we want to make it into more visuals, if we look at the graphs here, if, for example, if we take the t with equaling with ln y, if we imagine, if we take the limit, we take the limit of y, and then the t is getting closer to the infinity, or if you can think of the e to the x right here, okay. And you can also have the e with power of negative x. Okay. When you see how the e with power of x will behave, it will go through here and it will never reach 0. It's also the same, it will never reach 0. But I think so which means that when we have e with power of negative something, and there's something we need to change to, let's say, substitute a higher number, let's say to be infinite power, then it means that it will always going to be 0. Okay? It's always going to be 0. So 0 with power of infinite in indeterminate forms is always going to be 0. Okay? It's always going to be 0.
So this is just to prove that at the end, this is just to prove that when we have limit, where the f of x is 0 and g of x is infinity, this will always going to be 0. So the key points
Why it's 0 is because of the ln. Okay? Because the ln property, the logarithm property. If you think within the functions itself.
Okay.
Okay, so this will be n for now for the locus rule and indeterminate forms. The next part is the optimization. Okay. So the rest of this I will give you as an exercise, and maybe we can discuss a little bit next week.
So the next part is the optimizations. It's supposed to be 4.7 in your textbook, 4.7. And also include within your midterm topics. Okay. So optimization. Okay.
Before I drive through what will we discuss, from the word optimize or optimization, what is the description, or what do you feel about this word optimization? Is your life being optimized?
No.
Procrastination all the time. Working all the homework day before, one day before, or at least like hours before. Yeah, and then you feel like you go through social media and you feel like immersed into that world and then forget everything and then you play some games, etc. But the one thing about this optimization is actually, because we have learned before, some application on your in calculus, which is derivative, and in one part, from derivative, we can take minimum value, maximum value, right? That is about optimization. So what we are going to do is we are going to incorporate those maximum minimum value problems we have within real life problems, or some, it's not really real life, but in some way we can simulate, or design some problems into our optimization. And actually, if you can verify, or maybe naming your own variable, like in your life, you can optimize your life, right? Yeah, it's true. Like you can like decide what priority you will have, like 1, 2, 3, and what impact when I achieve this, what impact do we have, right? It's actually real life situation, right? But we need to simulate into some something that we can compute. Yeah, at least we can compute and we can have really good parameters. Right? Because if you like say, okay, I'm successful, but what is successful, right? You need to define, right? One thing to like necessary to define is we can define with numbers. Maybe like how many skills you have. We wrote one by one, right? And that's actually progress, right? That's progress. Or maybe you take some courses that you take, okay, 1, 2, 3, 4, 5, right? And that's good parameters. Instead just saying, okay, I want a good life, but what is good life? But you need to define that. Okay, so optimization.
So of course, the first thing, we will have a case, or problem. And always, this is always related to critical number. Okay. Always. The second thing, to understand the problem, sometimes you need to draw the diagram. And naming the variables. Three is find relation, formula, or models. Of course, in life, you could always find some models, right? Role models, maybe your parents, maybe somebody, maybe your senior. You can ask like how to get there, how to get to work on there, blah 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 blah. Right? It's actually, well, it's kind of relatable. Okay, and then last thing is, of course, after finding formulations, then you check its max or mean value. How to check that? Well, we need just to take first derivative and equaling to 0. And it always works, right?
Well, in our case, in optimization, it always works.
Okay, before we go through like examples that maybe requires to some definition and understanding, let me just give you like a simple process on how to relate all this four into our question. Let me write an example here. A simple example to just to describe this four. So if we have this much centimeter cube of material available to make a box with square base and an open top. Okay. Find the largest possible volume of the box. Okay. So let me underline all the necessary important points. So this we have the volume. Oh, not volume, sorry. It's supposed to be the area because we want to make volume. Yeah. Square, sorry. Yeah. To make a box, it has square base and open top. And asking largest possible volume. Okay, perhaps we start with the square. This, the volume of the box. In the box, and then it has the square base. So let's draw box, and the base is a square. So we take some time to draw. Okay. I think it's so let's say this is our box. First, we can name this box. Okay, we can name the necessary components. Okay, the first is the square. So maybe x and another x, okay, because it's square, and then the height maybe y. Okay. Just to note that it has different length. Okay, and then it has no top, right? It's open top. So there's no sides on the top. If we just write the volume from all these variables, we will have the volume is equal to x squared equal y.
And then we can write the area in terms of x and y.
Yeah? Yes.
Area of surface.
So we call this volume. This is this is what we want to optimize, right? This is our optimization.
Oh, and then we derive it and find
Yes.
But we have a problem because we have these two variables. So we need to find and relate the other variables and change into this, the one that we want to derive. For example, it says that we have this limit of material, right? So we can say that we can write a constraint. Okay, that's the 1,200 equal the area. If we look at this area, every side we multiply without the top, okay, then it will be x squared, right? X squared plus 4xy. Okay. We call this is our constraint. Okay. So either you are going to take x and change into y from this, or you can take y and then change to x from this constraint.
I think I will just substitute y with x, so we can solve this first. So let's simplify this. So x squared plus 4xy. So 4xy is 1,200 minus x squared, and y is divided by 4 is 300 over x minus x over 4. Okay, and then we take the volume is x squared and then multiply with this. Let's just solve this first. 300x minus x cubed over 4. Okay. Now to optimize, to find the largest volume, we need to find the critical point from this, let's say this is our new function. So we need to derive. So take it into our phi prime becomes 300 minus 3x squared over 4. To find the critical point, we need to equal this to 0. So 3x squared over 4 equal 300. This will resulting x squared equal 400. X equal plus minus 20. But of course, minus is not possible in our case. So we take x equal 20 centimeter. Then the largest volume well, you can check that it's true that the 20 is our maximum value. How to check that? Then we can just check using our this will be positive, this will be negative, right? So it should be like that. So x should be 20 and y should be, I forgot to write, it's supposed to be 10. Or maybe let me write completely for y. Y is 300 divided 20 minus 20 over 4. So 15 minus 5 is 10. 10 centimeters. So it goes through here.
the steps is always start with some process, some diagram, naming variable, finding some relations, some formulations. Sometimes the formula is given away, so you can just take that as your formula. And you need to find, is there any constraint given in the information that you can find, and then, because to make optimization, you need to have a constraint. You need to have a constraint. If not, then it won't be a optimization. You won't be able to optimize if you don't have any constraint. Okay, I hope the logic, okay, the logic, the process, I hope you can see the process. I think the difficult part is, if you have like, maybe the problem is not really appear to be that problem, so you need to like maybe read the question twice to understand. And I think, like the related phrase, this problem also I will maybe provide some clue, like maybe diagram, maybe what formula you need to use. And there is one thing that I'm afraid that not all students will notice in this optimization. Like, let me show you
What is that thing? Okay. Let me give you another example. So you have a wire with length 1 meter. Okay, cut into 2 pieces. Each piece encloses a square, which means you make a square from those 2 pieces. Okay. The question is find the largest area enclosed. It means the square, okay? The area of the square.
So we got 2 squares, yeah?
Yeah, we get 2 square. And find how we can maximize the area.
Area of 1 square or of both squares?
Both.
Oh, okay.
Both.
Okay.
So you have something plus another one, right? The square and square 1 plus square 2, right? But you will see some trouble, and if you understand the logic of this question. Just try first. Maybe in the middle, you'll think, maybe this question.
So it's like,
Maybe let me give you a diagram first, so you can maybe get more idea. So let this wire, okay? So 0, 1, and maybe you cut maybe here, okay? And let's say you have, this is x, and the other one is 1 minus x. So I'll give you the constraint. And this is the constraint, right? The constraint. So you have the square 1 with the 1 minus x over 4, right? Each side. And you have this x over 4. Remember, you need to fold the square, right? Fold, and you have 4 sides, and you will divide by 4. At least you have this. So if you follow through the questions, you can take the formula for the area. Okay, you can just plus these 2 areas. Right? You can take this, multiply, square. This also multiply and then square. Right? So x over 4 squared plus 1 minus x over 4 squared. And we can derive, and we can easily derive. It's not really a problem deriving this part, right? So this will be x over 8, right? Minus 1 minus x over 8. Remember that we need to derive like 2x over 4 multiplied by 1 over 4. And if you follow through this a prime equaling to 0, you will notice that we get 8 x plus x to x minus 1, and this will be equal to 0. And x is going to be half. This is supposed to be our critical number. And then, when we try to take this x equal half, we take into our equation inside. We take become this, and the rest is also the same. 1 over 2, 1 over 8 squared, right? And we got this is 64, 2 over 64. Or this is 1 over 32. Okay? But the question is, is this the largest area? Is this the maximum area? Yes. Right. It should be the minimum. So this has a problem with the question. The question should be asking the minimum. Okay, so here's the thing. All the question, if you have the textbook, all the question in the textbook, they all have the correct question. This is wrong question. So actually, if we think this x equal half, and we try to make our line number, and let's say this is maybe half, and this is 0 and 1. That's the constraint from the wire, right? When we take something here, maybe 1 over 4 and maybe 3 over 2, when we plug in here, maybe 1 over 4, and you see 1 over 4, 1 over 3, 2, 1 over 4, 3 over 4, it's going to be minus, right? It's going to be minus. It's going to be minus, and this is going to be plus. So it's going to be not a maximum, but it's a minimum value. Okay? That's why this confirmation is important. Okay? But for your textbook exercise, all the question is correct. I think it's correct. I'm just checking it.
This one is impossible.
Not really that impossible. We can do a little bit trick.
Yeah, we can take the smallest value.
Yes. So what we can do is, if you want to force the question the maximum area, we can take the limit. Let's say a fraction here, maybe around here. Take the limit as x approaching 0 from the right side of the function. And for sure, if we take 0 in our equations, it will be 1 over 16, right? The possible one possible number. So the answer is 1 over 16 with the limit. Okay, with the limit. But of course, in real life, it's not really possible. But in terms of limit,
we can force the answer to be 1/16, that's the minimum.
The maximum, sorry. The maximum.
Actually, it's the error if we don't cut anything. It
Yeah.
just will fall in.
Yes.
Yeah.
Yeah. The real life is like that. Okay. But of course, in math, you can have limit, in which it's not really that applicable to real life. So this is actually smallest possible area. So this has something problem with this. Problem in the question. Okay? This is just to show you that
Checking this line number from what we learned before the first derivative test is a necessity. Okay. I think I will stop until here. We'll stop until here. We are going to continue for more examples on optimizations, and I think either exercising the indeterminate forms, or maybe some discussion on other section as well. And also one more small section about antiderivative. It's still chapter 4, but it's going to be a bridging to chapter 5. Still chapter 4. We are not yet calling that as integral. We're calling that as antiderivative. So it's still derivative, but antiderivative. Well, it's just like the introduction to integral, but not yet integral.
okay, any questions?
Any questions? Maybe you guys found some questions, or maybe the answer key from the midterm that I gave you, the last midterm. Is it helpful, the answer key? No, really? Yeah, the next thing, so I will give you exercise on chapter 4. I already made, and maybe add something from the optimization. And also adding the link for the quiz is chapter 3 quiz. Supposed to be today, and the deadline around Monday night. So I think
You can choose which day. Okay. Okay. As usual, we are going to play the feedback game. Okay. Okay. I think I already checked the question, and I hope there is no mistake. Maybe I also check my side here. So if there anything that is wrong, I can correct it. Okay. Okay.
What's the meeting? Next week. 2 weeks.
Okay. So. Okay, write your ID. Okay, write your ID. Okay, let's start the game. Okay, 3, 2, 1.
I wrote the correct ID.
I think you can change the ID later. Don't worry.
No, I try to read this. They say don't put on. Yeah. I understand. Yeah.
Okay. Okay, the next one. Next one. Okay, who is Lobster and Skids? Okay. I think you can change your name at the end, okay, I think. Okay, next one. Okay, number 2. 3, 2, 1, let's start.
I think you need to see the screen for clear picture. I think this one in the projector is blurred, so I think better in your screen. Careful, be careful. You need to be careful.
Because I wrote instead of 10 words, so I'm messing up someone's score.
I think later you can change. They always like.
That's a friend.
Alright, good.
Okay, good, good. Who is lopside? Who is lopside? Is it a ghost? No? Okay. I think you can change your name at the end. Okay. One more question. One more. This is, I think, a little bit long. Okay.
Around 4 minutes. Around 4. Oh, ready? Submit answer. So you just need to type the x coordinate. Just the x coordinate for the input. And you can also do some shortcut if you want. You can write in the graphic calculator. Use some website or everything. And then you can observe from the graph. it has minus when you derive, don't forget to multiply.
Inflation point is 1 for second, right?
Yeah, we can check. You can check website. You can check graphics. Yeah, but the graphics will show you. Yeah, the graphics will show you the real proportions. So yeah.
那个0.多吧。
The answer is a really good number. A good number.
Really good number, okay.
跟零的话 x 本就有了，它都乘以一的早菜，
If the function maybe not easy to see the graph, maybe divide one time and check the graph. Maybe. Because the curve, the change is really small, really small. Yeah, I think zoom multiple times and you will see. Zoom and you will see.
它的效益，
You can see, right? You can see. I think before you see the.
这里。
哪里？边际。
Wait, the derivative. So let's run for derivative. Derivative should change from the f from x. So it's
Okay, it's one. Okay, it's one.
Okay.
Which 21? Okay, your student ID. Yeah, we check the graph with this question. Really small, maybe you will miss the inflection point.
所以那个尾跟那么透明，怎么尾啊？
you will say 2 b 1 1 2 but it's 1 2
刚那个尾巴。
I will say 251.
yes. And then you will see here that only 2 4 and 2.
Okay, you done?
And finish for today's class. Okay.